In our first lecture in the General Chemistry lecture series, we're going to go over the fundamental unit of chemistry, which is the atom and its atomic structure. Starting first with subatomic particles, or what comprises an atom. The atom is comprised of three parts: a proton, a neutron, and an electron. The proton is a positively charged unit that has one atomic mass unit of weight. This is located inside the nucleus, along with the neutron, but the neutron is neutrally charged, but it has the same mass. Electrons, on the other hand, revolve around the nucleus in electron clouds called orbitals. They have negative charge and a mass that is negligible. There's a distinction between atomic mass versus atomic weight. Atomic mass is noted as the mass number being the number of protons and neutrons within the nucleus. There's a very fixed number of protons because every atom's identity, or every element's identity, is tied to the number of protons it's comprised of. Therefore, if the number of protons changes, the subsequent identity of the element will also change. However, there is a fluctuating number of neutrons, which leads us to isotopes, which are species with the same atomic number, or number of protons, but a different mass number. This difference in mass number comes from the fact that there's a varying number of neutrons. This is usually identified by an element and a number. For example, carbon-12, carbon-13, etc. Hydrogen isotopes have different names: protium, deuterium, and tritium, as the prefixes suggest: 1, 2, and 3 in terms of weight, in terms of mass. Atomic weight, on the other hand, is a weighted average of all naturally occurring isotopes of a given element, and this is the number that you see at the bottom of each periodic table. It's a statistical average based on all the isotopes of that element, whereas the mass is for the respective element that you are looking at. Think about atomic mass as an individual, and the weight being an average. We've established our fundamentals, so for the next portion of this lecture, we're going to go into the discoveries and contributions of three gentlemen in particular: Ernest Rutherford, Maxwell Planck, and Niels Bohr, who are pictured left to right respectively. Starting first with Ernest Rutherford. Ernest Rutherford stated that atoms have a dense, positively charged center surrounded by mostly empty space. He concluded, based on a gold foil experiment, that this was so. The experiment listed simply stated that he took a source of alpha particles, launched them against a thin gold foil, and observed where they scattered. He noticed that, for the most part, these alpha particles went straight through, with very little deflection. The only thing that he could conclude from this is that atoms are generally just very much empty space. Maxwell Planck stated that energy emitted as electromagnetic radiation from matter comes off in distinct bundles called quanta. This would later become a fundamental principle of quantum mechanics, which puts energy in these concise quanta. His relation stated was energy equals h times f, h being Planck's constant and f being the frequency. Niels Bohr took up Planck's theories and he corrected assumptions made by classical mechanics. The Bohr model is what's commonly known as the model for the atom that we use today. Anytime you've seen an atom model in a textbook, you probably were looking at a Bohr model. It states that there is a positively charged dense nucleus with electrons in orbit at distinct energy levels. To the bottom right is an example of this. However, there can be multiple electrons in each level. He also denoted equations for angular momentum and the energy of an electron, which you need to have memorized for test day. Atomic absorption and emission spectrum rely upon Planck's concept that energy emitted or absorbed comes off as concise quanta. Absorption is when electrons go up from a low to higher energy level. Emission is the opposite, when it goes from high to low. This is going to put energy out. For absorption, you're putting energy into the system, and emission, you're putting energy out. The energy of an electron in motion is given by the equation below. To the bottom is an example of absorption and emission, respectively. These emission and absorption spectrums are very important when it comes to instrumentation and analyzing chemical processes. The quantum mechanical model of atoms simply posits that electrons don't travel in defined orbitals but in localized orbitals, basically saying that they don't have concise paths, which a lot of textbook diagrams show. Electrons simply don't move uniformly. They move randomly in localized areas, which is what quantum mechanics is simply stating. Because of this, quantum mechanics largely bases itself on approximations. Orbitals are noted as regions of space around nuclei that are defined by the probability of finding an electron in that region. If an electron has a high probability of being located in that region, then it's going to be stated that the electron occupies that orbital. However, they could randomly jump, theoretically, out of this orbital. The probability that I mentioned earlier is largely based on Heisenberg's uncertainty principle, which states that the position and momentum of electrons cannot be simultaneously known. This simply states that just by observing things, you are changing its behavior. Because of this, chemists have to approximate where these electrons are, which is where you get things like the Weissenberg theory, which models orbitals based on shapes and approximations. Going further into quantum mechanics, we're going to go into quantum numbers, or the numbers assigned to electrons. There are 4 in particular, the principal being the average energy of a shell, and it's the max number of electrons possible in a shell, and it's given by the equation below. The azimuthal is described as the subshell within said shell. This is where the denotations of sp, d, and f come from, which I'm sure you're aware of. The max number of electrons in a subshell is noted by 4l plus 2. The magnetic quantum number is the particular orbital within the subshell where an electron is likely to be found, and the spin is the orientation of an electron. A really good way to think of quantum numbers is to think of an apartment complex. The principal is the floor, the azimuthal is the room, the magnetic is the room within each apartment complex, and the spin is the person itself. So if you've got an apartment full of couples, you're going to want to know what floor they're on, what's their room number, what room within that room they are in, and who's there. So that's a very simple way to look at quantum numbers. When we look at electrons and shells and subshells, we have to take 2 concepts into mind. The first is the Pauli exclusion principle, which simply states that no 2 electrons can have the exact same quantum numbers. Each electron is functionally unique, just like everyone that you know. They can't have the same quantum numbers for this reason. If you see an electron on a MCAT question that has the same quantum numbers, you can very easily exclude that answer choice. Hund's rule states that subshells with multiple orbitals have to fill so that each gets 1 electron before getting another. It also states that half-full levels have unusually high stability. Paramagnetics are when there's unpaired electrons and that they're attracted to magnets. Diamagnetics is when they're paired and repelled by magnets. So an example would be, if they're paramagnetic, let me switch the ink out, there's an unpaired electron. So if I were to deal with a p subshell, if I were to have unpaired electrons like so, this would be paramagnetic. Diamagnetic, on the other hand, is when everything's nicely paired like such. When we're talking about Hund's rule, we're looking at subshells, like so. Quite simply, the subshells with multiple orbitals have to fill so that they get 1 before a second. So, instead of starting here and placing there, you're actually going to fill them 1 at a time, like so. Each one gets 1 electron before they get another. So you have to fill each subshell. You have to fill each one before you put in a second. If you want a real-world example of this, you don't have to look any further than looking at a bus or an airplane. When passengers sit on the bus or an airplane, they will generally space out before they start sitting next to each other. Electrons are very much the same. When we look at electron configurations, there are a couple rules. For starters, electrons have to fill from lowest to highest level. And there's an n+1 rule to help us with this. There's also a way to shorthand this using the noble gases. Let's do a couple examples. So, If I were to look at an element on the periodic table, and I'll just pick one, let's use oxygen. So we'll do the electron configuration for oxygen. Electrons fill from lowest to highest. So the first one is going to be 1s2, followed by 2s2, and then 2p4. This is going to be oxygen. 1, 2, 3, 4, 8. That's all 8 electrons, which matches oxygen's number. Now, when oxygen becomes ionic, there's going to be a little bit of a distinction because you're going to see the addition of another 2 electrons. This attains noble gas configuration, which is what all atoms strive to. So this is one example. Now, there's a shorthand where we can use noble gases to make it easier on ourselves. So how about we do silicon as an example? If we look back on the periodic table at position 10, you have neon. So I can put neon in instead of writing out 1s2, 2s2, 2p6. So I can start at neon and simply go into 3s2 and 3p2. So that's 10, 11, 12, 13, 14, silicon. Perfect. Now, if we were to look at neon, neon is just a shorthand for this. If you don't want to write this, you just write this little bracket shorthand. On the MCAT, you're generally going to see the shorthand, so make sure you know how to read it. Lastly, we're going to go into valence. As I stated earlier, atoms strive to achieve noble gas configuration, or a full valence. Valence is noted as the outermost electrons that participate in bonding. They're usually s or p orbitals, or in the case of hybridization, a mix of the two. When you look at transition metals, though, it's either the s and d orbitals. F orbitals are a little bit more complicated, and you'll likely not see them on the test, so I wouldn't worry about them too much. Most atoms will bond to complete an octet in the valence shell because of this principle. So if we were to look at 2 atoms in particular, so let's do sodium and let's do fluorine, for example. Sodium has 1 electron in its valence, whereas fluorine has 7. Both of these want to fill their octet, so if you put these next to each other, sodium is going to have an easier time getting rid of this electron than it is trying to get 7 others, whereas fluorine is going to have a better time gaining an electron rather than losing the 7. So the result of this is that sodium is going to lose this electron, give it off to fluorine, achieve a happy full valence, and fluorine is also going to get a full valence. So both of these guys are going to be happy. Alright, so that covers some fundamentals of general chemistry, in particular atomic structure. These principles are going to apply for every chapter moving forward, so make sure you have these down. In the next lecture, we're going to go into the periodic table and its trends.